Hi, this is Kathy Jakisic, editor of Healthcare Facilities Today. Thanks for attending today's webcast. Learn the building blocks of a power monitoring system and how to yield big benefits from the information. Our presenter today is Jim Topher, Healthcare Segment Manager for Schneider Electric Digital Power. Jim works with healthcare organizations, specifiers, and contractors to develop and implement innovative energy and power management solutions. These solutions deliver improved energy efficiency, a more resilient power infrastructure, and ultimately, an improved environment of care for hospital patients and staff. Jim has 32 years of energy and power management experience and is both LEED accredited and AEE certified. He also holds an electrical engineering degree from the University of Florida. Today's learning objectives include: identify the capabilities and choices available when designing a power monitoring system, analyze the key benefits that a well-designed power monitoring system can provide for a healthcare facility, understand how digital architecture creates a more powerful IoT environment, review how power data can be applied to lower operating expenses and capital construction costs for hospitals, and assess how analysis and reporting from a power monitoring system can identify and eliminate infrastructure vulnerabilities. Before we get started with today's webcast, I'd like to cover a few details about today's event. A live question and answer session will follow today's presentation. To submit questions, please use the Q&A panel on the right-hand side of your screen and send your questions to all panelists. At the conclusion of today's webcast, you will receive a link to download a PDF copy of today's presentation slides. You will also receive a link to a brief online assessment. Upon successful completion of this assessment, you will receive your CEU certificate. This webcast will also be archived at healthcarefacilitiestoday.com. And with that, I'll turn it over to Jim.
Great, thank you, and good afternoon, everybody. This is Jim Topher. The presentation is divided into two parts, really. The first part is building of the power monitoring system and looking at the piece parts and best practices. The second part, which is my favorite, is really how to use the data and get really some of the benefits and savings. So jumping right in with the building blocks, where healthcare is different is we have different objectives, different needs. Everything that we do is first centered around the need to improve the environment of care. It's about the patients, the occupants, the caregivers, and everyone that's involved. So we want to make sure that we're delivering value for that objective first and foremost. But also, one of the things that we want to be able to do is provide utilities and resources that improve worker productivity, how to do more with less. Part of that also includes shortening response time. So what's happening? What does it mean? What should I do? And then last, but by no means least, is delivering cost savings. So how do you really take the data and make it actionable, and how do you measure and verify savings? So starting out with the meter selection, the first thing that you'll see once you start down this path, there's a lot of choices. It's not a one-size-fits-all approach. There are many different types and grades of meters. You can see on the right-hand side, we've got some specialty meters, multi-circuit, and things that are, specific to retrofit. But then in the metering, there's really three groups or three types. You have basic metering, what we would kind of term intermediate, and then advanced. If you can see down along the horizontal axis, you have price. So as you have more features and capabilities, there also is a higher cost that comes to that meter. So I say choose wisely there. You don't always want to go with the lowest cost for that simple reason. But there's a strategy and approach that can be applied to get the most out of your investment. So when comparing these different categories of meters, these are the criteria or the ways that I would separate them into these buckets. And the first thing we start with is, what is the accuracy of the meter? So if it's a 0.1 to 0.2% of reading accuracy, that's considered very good, and that would fall into these advanced metering categories. Kind of in the mid-range is this 0.2 to 0.5%. And that's still a very good meter, still provides very accurate readings. If you're simply doing energy submetering, it would then fall into this basic meter bucket. And when you're looking at accuracy for those types of meters, you're always looking for a meter that's better than 1% accurate. Anything less than that, if you were challenged on the readings or the value, you may not be able to say, look, here, this meter is accurate enough and it is capable of standing up to scrutiny. So, you know, you want 1% or better for energy, and as I said, you want to have higher accuracy where you need it. And what really helps to achieve that accuracy is the next category, which is the sampling rate. So you have analog voltage and current waveforms that are being sampled and converted from analog to digital inside the meter. And the faster the meter does that, the more accurately it's able to create that sinusoidal waveform, plus any harmonics that are distorting that. And so you can see the fastest sampling meters are generally around 1024 samples per cycle, not seconds. So it's very, very fast. In addition, you also start looking at the architecture of the metering and the network and the software, and you start looking at how is data managed. And the thing called onboard memory and the ability for the meter to capture data, to store it, and then to transfer it to a host becomes very important. So the advanced meters tend to have a large amount of memory, not only for data logging, but also for disturbance, waveform captures, and things like that. As you get into the intermediate and the basic, you tend to either not have onboard logging or have substantially less memory for that onboard logging. After the waveform capture, which is really associated with events or conditions that you want to be able to document, one of the great features about advanced meters is this disturbance direction detection. And we actually have an example of that I'll go through later, but it helps you not only see what occurred, but it points at, well, where did it come from? And that's just very important when you're trying to identify why did it happen, what did it do to us, and how do I prevent it from occurring again? We also then look at inputs and outputs, and whether or not we can look at the status of equipment, or we can look at other types of information that may be available either as a digital or as a analog input, but it isn't necessarily electrical, like potentially if you wanted to monitor other utilities like water or gas or steam. And then the programmability is the last point. Advanced meters have a lot of flexibility, so you can completely tailor them for what you're trying to do, or something that may occur in the future you haven't thought of yet. So that's the basic differences. Here's how I recommend they're applied. So your advanced power quality metering in a hospital setting, in my view, should always be utilized for hospital normal power mains and for generator mains. That's where power quality starts, is at the source. And if that power quality is poor, all of your loads are going to suffer. So it's very important. If you have vulnerability, existing conditions, or there's concern for your imaging and medical equipment, it can also become a very wise choice to incorporate the advanced metering on those circuits as well. When we start looking downstream at key distribution feeders and things like transfer switch loads, that's where the intermediate meters are typically applied. So you've got high-end power quality meters feeding more of the intermediate meters down in the distribution and at the transfer switches. Down on the multi-circuit specialty, you see on the right-hand side, I mentioned operating room isolated power. That's another unique thing to healthcare, where we have the requirement in wet areas delivering patient care that it either needs to have ground fault or isolated power. Where you have isolated power, we do have the ability with power monitoring systems to also be able to monitor that, know the total hazard current, and if a dangerous or hazardous situation is there, all of the data is logged, stored, alarmed, and you notify the appropriate people. And then, as I mentioned on the previous slide, there are also multi-circuit devices that are often used for tenant submetering. And we'll show some examples of that. But typically, if you've got a panel board or a switchboard, you've got the need to meter many circuits within that rather than having individual meters, there now are multi-circuit meters that can be applied. The other quick criteria that you maybe want to be aware of is that meters do come in different form factors. And, quickly going through these, you see number one looks a lot like the meter on the building or maybe on your home, and that's an under-glass utility style meter. Other styles of meters are shown, whether they are mounted on a door, mounted inside the enclosure, if the display is remote. But then we get to number 5 there, and that's the idea that we can incorporate intelligence within power distribution equipment and power equipment in general. So that's actually showing a breaker that has a smart trip unit, allowing it to communicate not only the protection information and the open close, but it also has the ability to do power and energy monitoring as well. Down below, we show the multi-circuit meter, which is number 6. So you see strips of current transformers. So individual circuits can be monitored. A voltage gets connected to that, and it has communications. One thing to always keep in mind with those types of meters is all of these circuits need to be from the same source. You would not want to put this as a meter to monitor circuits in different panels. Generally, it's everything within that panel is the way that you would go, and it's all from one common voltage input, single phase or 3-phase. And then 7 and 8 are kind of a retrofit and a panel board plug-on style. So 7 is showing the current transformers and voltage that go to a metering embedded inside of the CTs themselves. So there's a lot of convenient ways of retrofitting metering. And then the final one there, 8, is an example where the metering has actually been built into a module that plugs on like a circuit breaker in a panel. And those are being called in the industry smart cells. But it does help you avoid having to extend either the side or the tops or bottoms of your panels in order to be able to fit metering. So there's some innovative ideas out there to help you solve your problems. When you're looking at new equipment, all of these different types of equipment are places where you should consider metering. Obviously, your power equipment, you want to be able to service and, meter your services, both your normal power and your generators. If you have multiple generators, you may very well have paralleling equipment. That is the perfect place to have smart meters that can communicate and tell you everything going on. But then we also need to take into consideration fuel systems and batteries that are serving the generator. Want to make sure that we know the state, if there's any alarms, the amount of fuel. And if we're monitoring generators and fuel systems, it's pretty common that we can also be able to calculate the available runtime with the fuel available, which can be very helpful in a crisis. Down below, we're showing transfer switches. And again, the OR monitoring panels that I mentioned earlier. Those are ideal places for metering to be incorporated. In fact, in many of the OR panels, the metering communications is normally standard for most of the industry providers. On the far right-hand side, we have UPSs and power factor, power correction, power quality correction devices. It's always important to maybe first meter and determine your need for those things. And then based upon that, you can apply the right solution. And then you monitor to make sure it's delivering what you need, to make sure there's no maintenance issues. Certainly if you have power factor correction, for instance, you don't want to find out the unit isn't working properly by getting a high bill the next month. You want to know in real time whether or not it's solving your problems, and all of that is doable. So just a quick look, if we do have equipment that's being supplied with these meters, this is where you would see them. So on the left-hand side, this is your low voltage equipment, or basically 600 volt and below. So you normally would see your individual meters, you'd have your communicating trip units, and then in some cases you may have these smart cells that are plugged in like breakers that actually include metering. On the right-hand side, we've got medium voltage gear or switch gear. And so there we would be looking at protective relays. Again, you'd have individual metering. We would be able to monitor the temperature of the transformers. And then on the low voltage side, again, you'd have meters and trip units. So a quick note about retrofit. Showed you a picture there of the new equipment, but when you're retrofitting, there's three considerations that every meter is going to involve if it's part of a power monitoring system. You're going to need voltage to measure from the circuit being monitored. You're going to need current inputs, which normally, almost always will involve current transformers or CTs. And then you need communication so that you can remotely be able to read and acquire all of the information being captured by that meter. When you're looking at the voltage supplied to that meter, you have to power the meter as well. So a common practice is to simply use the voltage input from the circuit you're monitoring for control power to the meter itself. In critical applications, you often want to avoid that, and you want a separate continuous control power source. If there should be a disruption in power, you want to be able to have the meter online and be able to communicate and be able to see what's going on remotely. And if your meter is powered by that voltage, it'll simply go offline. The way that that's typically done is through UPS power, and the UPS can either be existing or in these enclosures, a separate small UPS can be provided for that continuous control source, but it's very important to think about that. A quick note on safety. Whenever you're dealing with metering being retrofit, it is strongly advised, if not insisted upon, that those be on de-energized circuits. And I know in healthcare that's always a challenge. That's why you should always try to incorporate it in your brand new equipment. But where you are retrofitting, please be very cautious of energized circuits. Whenever you have current transformers, be sure that you have shorting blocks that are installed for those. So in the future, if you do need to service that meter or any of the circuits inside, you have a way to safely do that. One thing that I have found over the years, 32 years plus, is you have to be very aware of what your authorities having jurisdiction will allow you to install in different equipment. And in some jurisdictions, they may require a separate enclosure for the meter rather than it being retrofit in the field into power equipment. Again, new equipment, it can leave the plant, it's got a UL label, and usually that goes very, very smooth. When you're retrofitting, they may be requiring, in some cases, that equipment be refield certified by UL, and that can be very costly and something to avoid. And again, seeing the separate enclosures that we show up on the top right-hand side, it's industry available, so that might be a smart approach whenever that comes up. One other quick note, I did mention the CTs. I show a couple different types here on the bottom right-hand side. You see that there is a split core where one of the ends of the CT actually snaps on and off, so you can slide it on conductors. And then the other side on the far right side is a rope CT, which is actually what's known as a Rogowski coil. But it's a flexible rope that you can loop through the conductors to make sure you've got everything connected. It's very flexible. It is a little more expensive, but it can solve some big problems. So there's a lot of technology there. So we've got metering, we've got it installed, and now we're going to start looking at the architecture of the system. And, you know, the Internet of Things in healthcare. So we've got devices, systems, and the ability to do analysis. As we start looking at power systems, it's the same approach. So we have connected equipment, we have both on-site systems, and then we have apps and analytics that sometimes are cloud-based, but they allow you to see what's going on beneath the surface and make decisions. The architecture that is best suited for that approach is what we're showing here. And it's a stack that begins again with a connected product. So here on the bottom you see you've got your equipment, your breakers, your meters, all of your infrastructure that's communicating through a network. The important part of that are the 5 things on the bottom: secure, open, scalable, flexible, and future ready. So you want to look at certain criteria, and I'll go through some best practices as I wrap up this part of the presentation. But those devices are going to go through a middle level that's sometimes referred to as the edge control. And those are the local monitoring systems, whether it be the power monitoring or the building management system, or both, that are able to utilize that information and provide benefit to the occupants and to the users of the system. But then, as I mentioned, you can take the data and do some very in-depth analysis and provide reporting and insights beyond that. And that's that top layer where you're able to provide the apps and analytics. And so that's the architecture that ultimately you want to be pursuing whenever you are building your power management system. So I mentioned it before, some top 10 monitoring design tips, and this is, I guess, through the years what I've taken as, you know, what are the right things to do and what are the things to avoid. And I'm starting with one thing to avoid. Avoid unproven or proprietary systems. To some extent, you know, choose partners that have been doing this and know what they're doing and can show you other customers like you that have systems that are providing these benefits. New technology is great, and maybe try it, but I would avoid anything that is totally proprietary, and you need to be able to share the data and keep that architecture that I showed a minute ago in mind. Number 2, keep track of what it is you've got in your facilities. A lot of times you have equipment that's ready to connect. You just don't know, and it's sitting there and you're not getting the benefit. So try to develop and keep a list of all the assets that can be incorporated. Number 3, try to utilize smarter devices. So where you're able to incorporate this technology, you want to be able to look at that onboard logging and those other sorts of capabilities so that you're able to collect that information and share it with systems. Number 4, don't underestimate the benefits of power quality metering. And I would advise strongly on your normal and emergency mains, those should always be power quality meterers, just so you always have the ability to see how am I doing, what's working, what isn't working, and if there's any impact to my facility and my infrastructure, is it related to power quality? And kind of tied to this where, you know, in your meter selection, keep in mind that the cost of the meter is only one component. You also have an installation cost. And you may save a little bit, but if the meter isn't the right fit or doesn't last very long and you've got to install something else, that installation cost is very significant. So you want to do it, try to do it right the first time. The number 6 item here ties into some of the things I was saying earlier with the new equipment. If you want to make sure your dollars are going as far as they can on your new construction work as well as your other work, try to make sure your design specifications are up to date. it isn't uncommon that I'll look through design specifications and see that they've got obsolete products listed or maybe conflicting requirements. And frankly, when contractors and manufacturers have confusing specs, they seem to respond to that with contingencies rather than giving you exactly what it is you want. So try to have that up to date, and certainly ask experts for help. Ask the different power monitoring companies, the different consultants and specialists to review the specs and provide you with their recommendations. The seventh item is more and more important. Get your IT engaged right from the get-go. If we're going to take advantage of IoT and technology, they're going to be the gatekeepers. And if they're on your team, things go much smoother than if they're brought in later and are confused by what it is you're trying to do. Number 8, think about the analytics to try to get more and more information from your data. A lot of data is a lot of data. You want to be able to act and understand that data. So look for opportunities to have that better analyzed. Number 9, which could be very well number 1, build a team. So we all are busy. We all have expertise that varies, and together we can build something that will really suit your needs as a team. And then number 10, when you do have these systems and you do experience things that occur, try to document them. And that's the next part. I'm going to go through some documented case studies, but it's important. It gives you an opportunity to show off what you've done and then share it with your peers so they can see, ways to get benefits as well. So then in part 2 now, I want to be able to get into some real examples. And they fall into these 3 categories: availability, safety, and efficiency. So I'm going to go through these 4 examples of how power monitoring systems were utilized to actually find either savings or vulnerabilities, and how that really played out. So in a monitoring system, it's very typical that you'll be able to see your real-time status of your system. So you'll be able to know, are breakers open and closed? What's the loading? Are there any issues? And so one of the very cool things about a monitoring system and the disturbance direction detection that I mentioned earlier is when a disturbance does occur, it'll actually point you to where the problem happened. So we can see here at the main, there we go, that there was a fault and it was downstream. And we see from the feeders that they were seeing it upstream, except this one right here. And follow it, and you can see the fault location is pointed to, so that immediately all of the technicians and those that are responding know that something's occurred, and they know where it occurred, and they know which direction it came from. So that was a real event, and this is what they found. So here you see a picture on the left, and then I've zoomed in the center, but a variable speed drive had failed, and a lot of black soot and smoke. And so the first thing is, how do we get back into service? The next thing is, what happened, and how do we make sure it doesn't occur again? And so kind of the way this played out is how you'd expect. Get a equipment manufacturer saying, hey, man, you got dirty power. And you have the utility saying, well, we didn't see a problem. And so the finger pointing began. And the power monitoring system is where you can really start to get insight. And so rather than what you think occurred or what you wished occurred, we can show you what really occurred. And so this is the actual alarm log showing that there was a disturbance and that it was detected as being downstream by the disturbance detection in the meters. And the waveform capture, you see the actual fault current exceeded 10,000 amps. So the manufacturer made the very good point that power quality is not a single event all the time, that you could have a lot of little events that over time degrade your equipment and lead to failure. And so the other very important thing that the power quality meters do is they track power quality over time. And this, what I'm showing you, is a standard kind of plot for power quality. And it's based upon what's known as CEBIMA. And CEBIMA stands for Computer Equipment Manufacturers Association. And in a CEBIMA curve, what you're looking at are these events. And each event is plotted, and it's based upon the magnitude, where 100% is nominal, and you can see 100% is right in the middle of this envelope. So you have magnitude, 100, 200, 300, 400, 500%. And then on the horizontal axis, you have time. And so systems that include sensitive electronics can withstand short duration events, but the longer the event, the lower the magnitude that can be rode through. But what we see in this particular plot is that all of the power quality events that had been observed are within that envelope of acceptable power. So according to the data, the equipment failure in this particular case was not a result of power quality. This is another example just to give you a comparison. This is what dirty power does look like. So this is an actual event. This shows power quality events during the week of Hurricane Irma in Florida. So all of those events that are shown in red dots, those are ones that are at or outside of the acceptability. So certainly equipment damage and disruption would be expected looking at something like that. But going back to this previous slide, providing this information back to the manufacturer, the outcome was they covered it as a warranty, saving the facility thousands of dollars. So if you have the data, whether it's the utility or the equipment, if you can demonstrate through data where that issue came from and why the event likely occurred, many times you can get help and financial help recovering and repairing. So the next thing that I want to go through is how to take information being collected by your equipment and your metering for your emergency power supply system, or your EPSS, and to use that to automate your compliance reporting. So currently, or maybe for some in the past, but still for many, the manual method is used. So a technician or multiple technicians are taking values, going to equipment, checking, making sure everything works right, but mostly making sure they've documented that monthly test. And so all of that now, utilizing the monitoring system, can be automatically collected, automatically stored and put into reporting, and then it can be verified to make sure that it's following all of the right standards and is compliant. When you're looking at, well, which equipment gets brought in, it's what we reviewed already, but just for a quick update or a quick look again, we're looking at the generators, the main power distribution from those generators, the transfer switches, and then you may want to bring in, again, your fuel systems, potentially your batteries. And if you've got some local enunciation, many times that can be very helpful to have access to that information as well. All of it should be networked into your system so that over either at the facility or even in some cases remote from the facility, a power monitoring system is capable of capturing the information that's been gathered by the meters and then returning the reports that can be used for the documentation, but also can be used to make sure that everything was done correctly and identify if there were any other vulnerabilities. So this is a part of the report that's probably the most often viewed. It's whether or not it passed or failed the generator monthly 30% for 30 minutes. And what you're seeing here at the top left-hand side, we do have a plot of the KW of the generator logged continuously over that time and verifying that there was a minimum of 30% for 30 minutes. There is another alternative method that's accepted by most AHJs, and it's certainly in NFPA 110, is the generator exhaust gas temperature can also be used. So there could be instances where you're not able to reach 30%, yet your exhaust temperature may actually be above that minimum, which means that your monthly test would be a pass, and you would not necessarily be required to do annual load banking. Another very important part of the reporting is the sequence of events and showing you all the summary of everything that occurred and when it occurred. And here's a quick example that raised the flag real quick. And you look at where I'm showing the first 3 events were test status from the same ATS. So in other words, the technician went up to the transfer switch and attempted to initiate the test there 3 times before the generator started running. And seeing that raised the flag, okay, why didn't the generator start on the first attempt? And what was found that the generator had actually been left in manual mode. And the technicians didn't realize it until minutes later. And the question needs to be asked, well, if it was in manual, what if nobody had noticed for days or weeks later until there was an actual event? And so what this really identifies by having this sequence of events is whether or not your system is not only performing according to the standards, but do you have the awareness of your vulnerability? So in this case, the generator was in manual, and yet the facility didn't have the alarm enabled so that they would be able to know that. And then the last 2 examples are really going to get into how do I find dollars that I can save with a power monitoring system. And obviously the first place to look is your utility bill. And the 2 sides of that, number 1, do you know how you're paying for power? If you know that, you can develop strategies on your consumption pattern, how you sequence loads, things like that. And many times you can realize energy spend reduction even if your energy consumption did not go down. And the key part of that is also knowing within a healthcare facility, well, where is most of the energy being used? And what you find in a typical hospital, 72%, nearly 72% on average, of the energy being consumed is in the mechanical space, and most of that is HVAC. So you're looking at your utility bill, and now you have data from your power monitoring system. When there's a customer-owned meter that is looking at the same circuit as a utility meter, we sometimes refer to that in the industry as shadow metering. And what we're doing is we're seeing, do our measurements match the utilities measurements? And when there's a difference or a variance, we want that to be something that's brought to our attention. It is not unusual at all to find systems where there could be mistakes. So when you do find a mistake, what do? The first thing that you do is you make sure, are you indeed shadow metering? And we have found that customers had circuits going to other places that they didn't realize, whether it be some office building or something like that that they didn't realize was fed off of that same circuit. Secondly, could there be a wiring issue either with your meter or with the utilities meter? Usually those things show themselves pretty early on. You'll install your meter, you'll see a big difference with the utility meter, and you'll find out a problem exists. And once it's corrected, you may be able to yield some savings moving forward, but certainly you may be due some refunds going backward. The other part is you want to look at the charges on your utility bill and see, well, what can I do about it? And the two biggest things to look at is, number one, your demand charges, and then where you're in an area where power factor may be charged. There's big opportunities to improve or manage those using the data from power monitoring systems. So here's an example for demand. This is a real trend from a children's hospital where they experienced a very large peak demand, but it occurred 3:15 a.m. And obviously looking at that, you're like, okay, what did this cost us? Why did it happen? And what can we do to make sure it doesn't occur again? And so with the data and the report from the monitoring system, it's very easy to see what was the actual demand that was charged. And here we see that demand charge was actually $14,000. So it's like 27% of the monthly spend that month. When we look closer at it, we saw that actually there was a loss of power and then a restoration of power at 3:15 a.m. So we started looking at, well, what was going on at 3:15 a.m.? Why would that have occurred? And what we found is it was actually part of their maintenance and testing. And their restart procedure for their facility was not working right. So all of the loads were turning on all at the same time. So that's a simple fix where by simply better sequencing the loads, they would be able to avoid that expense. And then the final example that I want to give you is what and many would just refer to as right-sizing equipment. In my experience, much of the power equipment in hospitals is dramatically oversized. So here's a real quick example. This is a project I've got highlighted, a transfer switch feeding a new panel board. And we're going to look at calculated demand versus actual demand. So, a little bit of explanation. This is on the example of a existing panel and whether or not you have to make it larger or make a change. On new equipment, you would always follow NEC procedures and methods for calculating load. But where you've got existing circuits, using existing data is not only good, it's recommended. But in this example, you can see that the circuit, that panel that the transfer switch is feeding is sized at 128.55 kVA. But when we look at the actual data, we see the maximum ever recorded on it was only 39 kVA. So what we're looking at here is the ability to avoid equipment that would be 3 times larger and 3 times more expensive than needed. So there's an opportunity here using the data to derive savings in your capital expenses. So those are that's kind of our recommendations or ideas on how to put together your monitoring system, the key parts of it, and then how to find these opportunities using the data for availability, safety, and efficiency. So thank you very much.
Thanks, Jim. And we do have some questions here, so I will launch right in. One of our attendees wants to know whether you can offer any recommendable products for power monitoring. They've been looking for quite a while and have not been successful in finding any. Well,
certainly if my contact information is available, please reach out to me and I'll guide you in the right direction. There are plenty of companies, including Schneider, that have a full line of meters and systems. I'm I'm kind of assuming that they meant power monitoring, but if it is other utilities or other things as well, there's certainly those solutions as well. So if you want to lead them to me, I'll make sure that they get taken care of.
Will do. Next question. What logging interval do you recommend for energy or power metering data? And is this interval the same as a PQ logging data? Note that they are not referring to the sampling rate, but the file storage interval for analysis and reporting. For example, they tend to expect a logging interval of 15 minutes, which is equivalent to the timing interval of their electrical utility meter data. So can they shadow them in sync for auditing challenge purposes, provided revenue grade quality?
Wow, that's a long...
Yes, it is.
Somebody types good.
Yeah.
I think I can answer it pretty succinctly. So for energy monitoring, you do want to have interval data, and generally that interval is 15 minutes. If you want to make sure that your interval and the utilities interval are matching, that's where you use an input on one of the intermediate, and even some of the basic meters can do that, but certainly the advanced meters. So you would use an input that would use a sync so that your interval for collecting that is the same as the utilities. If you don't have that, generally what the metering will do is it will collect data on every 15 minutes on the hour, and it time syncs so that it is always accurate to whatever that time sync source is. It generally is the server or some other device that's meant to be the time sync. So in general, your energy logging is 15 minutes. I don't know if it was asked, but I do often get asked, how long do I need data before it's meaningful if I'm doing reporting or even if I want to do some energy modeling? And typically you want at least 12 months so that you have every season. And then if you've got it, 2 or 3 years is great for doing comparisons and modeling. And then finally, for power quality, it's not a good strategy to log everything all the time constantly. It's actually very inefficient and it bogs everything down. What you want are those smart devices that have the ability to log on exception. So when an event occurs, you do take data logging very quickly. You can have a much faster interval, in some cases many times a second. In addition to that, you can do the waveform capture. So you log on exception during conditions and events, and then you do your interval logging. And all of that occurs within these smart meters automatically without the operator having to intervene.
Thank you. Next question. What did you mean by right size equipment? What will happen if the requirement goes up during the day?
Well, what you're looking for and what the National Electric Code and many AHJs are requiring is load profiling over, in some cases, the previous year. I know in some jurisdictions they're looking even only the last 30 days. But what you're trying to identify is what is the actual maximum that has occurred. And if you are designing and you're designing equipment 3 times larger than that, I think that could be in many cases oversized. So right sizing to me just means that you have enough capacity that you can handle the requirement plus whatever growth you're anticipating. But in many cases, given budgets and the small space within rooms, if you can size more appropriately, you're going to have a better outcome with your footprint and your budgets. So that's what I mean. And I know if it's new construction, you are very limited because there is no existing data. But if you've included metering, then the construction projects that follow it, where that circuit is going to change, maybe loads are being changed or added, you have that log data to see, does the capacity of the equipment existing, do I have the ability to utilize it without replacing it or expanding it if I don't have to?
Great. Next question. At what percentage of full amp rating of a CT does one lose accuracy due to being oversized relative to the measured loads? He's seen this for meters with CTs sized for switchgear nameplates, yet the actual loads were much less.
Okay, so at first when you started the question, I was thinking on the high end, and now I know that they're probably talking about the low end, so I'll address both. So normally, for many meters, you have a minimum amount of current that it needs to detect, remembering that you have a system where you are using current transformers, generally 0 to 5 amp, and you are measuring the current and trying to have an output that is that represents that from 0 to 5 amp. So if you have a 1,000 amp CT, it's not unusual that below 5 amps, it's very hard for the meter to detect that, excuse me, and be able to measure that accurately. So generally, some people even say 10%. I would say the accuracy below 10% loading can be an issue, certainly below 5%. If you are exceeding 100% of a current transformer, you can saturate the CT and get a bad output. You also have a clamping amount on your meter. So if you happen to notice in the example that I was showing with the variable speed drive, where there was a 10,000 amp fault current, you could see that it flattened at the very top. And that's where the meter actually clamped that input so it wouldn't damage the meter. So there's a couple of moving parts there, but the rules of thumb, you don't generally want to exceed 100% loading or less than 10% loading of a CT in most cases.
Okay. How do I determine if my hospital's existing power distribution equipment has meters or intelligent devices that can be used in a power monitoring system?
Yeah, and that goes back to the best practices. One of the first things that I said is to have a list of your assets and your meters and your smart devices. If you don't have that, or maybe you're new and this is a new facility for you, the best thing to do is to conduct a survey and to look at all of those strategic points that I'd shown, the normal mains, the emergency mains, the transfer switches, the medical equipment, and then where your energy consumption is very large, so your chillers and other equipment like that. And what I would offer is it's not, I do a lot of surveys for a lot of customers, so if you would like to utilize the same forms that I use, I'd be happy to share them with you. So just give me an email, and I'd be happy to share the survey forms that we use so that you can collect that information and know what's available for a power monitoring system.
Great. Do power monitoring systems allow control of our equipment, and what if we don't want that to be allowed?
Yeah, that gets into security versus convenience. So most of the modern power monitoring systems, if they're designed properly, they have a view-only interface, and typically it's web-based. There's also what's called engineering clients. And an engineering client can be installed on specific computers and configured for secure control. So if you only want view-only, you simply don't install those engineering clients on the computers, and that's how you would manage whether or not anyone would be able to control equipment and whether or not they have the credentials, and that way nobody can hack in over the web and control your equipment as well.
Great. And what is the recommended amount of data that should be collected by the system? How many months are needed? How frequently should they log the data? And finally, where is it stored?
Yeah, and that's similar to the other question. So again, 15 minutes is the typical interval for your energy management logging, and that would be for your, absolutely your kW demand. You would want to log that frequently. Your energy, it would be good, but typically amps, volts, power factor. Those are generally logged every 15 minutes, and ideally they're logged on board the meter, and then the meter takes that, collects it, and sends it back to the monitoring system host. The other parts of that, I think you asked how many months. As I said earlier, generally a full year is desired so you can see all seasons. That's also what's recommended in the National Electric Code. If you're doing modeling, you typically want multiple years so that your calculation and your equation can be accurate. So 2 to 3 years is nice. And then the last part, I think, where is it stored? So I mentioned the meter is storing it, but once you get into the software itself, it generally is stored on board a SQL database. And that can even be a SQL database that's part of the customer's SQL cluster. So the part of the challenge that comes with these monitoring systems is you also have to have a pretty good bench that can help you with the IT side. And that goes back to picking the right partners and working with the right people, because there is an IT component. And certainly working with your IT group and understanding their requirements for a SQL database becomes a key part of this.
Thank you. We have a couple more questions, but they're pretty specific, so I'm going to let you answer them offline. But I wanted to thank you for your great presentation and also thank our attendees for being with us today. So everyone, I hope you have a great afternoon, and look for that email with the slides and the assessment.
Very much.